This chapter we're going to be taking a look at gases and the property of gases and the equation involved with working with them. First thing we need to do is identify or define ideal gases. We're going to be working with ideal gases for the most part of the chapter, and when we talk about them, we talk about them as being ideal because we treat them as particles that have mass but no volume. In general, the container size is many thousands of times larger than the particle size, and so they're effectively without volume inside the container. We treat gas particles as having elastic collisions, and what that means is when they bounce into each other, when they bounce into the walls of the container, they bounce off, transfer their energy, but no energy is lost. Either one particle has it or the other particle has it, but none is lost due to friction or compression or things like that. The third property of ideal gas particles is that they have no attractive forces. In general, the particles are so far away that even if they are strongly polar, they are not within range to allow those attractive forces to exert any pull between the molecules. So when we deal with ideal gases, we treat them as having those characteristics. All gases follow these definitions when they are under low pressure and high temperature. Low pressure would be atmospheric pressure. High temperature is essentially room temperature, especially when we're talking Kelvin scale. Gas pressure is created when the gases collide with the walls of the container. And if there are more particles, there will be more collisions and the pressure will be higher. Or if the particles are moving faster, they'll collide more frequently with the container walls, and that will also give us a higher pressure. When we talk about gases and when we use gas equations, we need to talk about what are the standard values. Standard temperature and pressure is what STP stands for. These are values that you should be familiar with. You've seen them hopefully in the first year chemistry, you've used them. They are on the green sheet, but it's useful to know them. Standard temperature is 273 degrees Kelvin. That's equivalent to 0 degrees Celsius. Volume of a gas at standard conditions is 22.4 liters for 1 mole of any gas. Standard pressure, we have 3 common units of pressure that we use when we're talking about gases. We have kilopascals, atmospheres, and millimeters of mercury. There's also torr and bar and pascals, but these 3 pressure units are the ones that we use most frequently. R is the gas constant, and the value of R depends on what pressure units you're using. So for kilopascals, the value for R is 8.31. The units for R are volume, liters, times the pressure unit, over the quantity moles times the temperature in kelvins. So when we have atmospheres for our pressure, our R value is 0.08206. And when we have millimeters of mercury, our R value is 62.36. So again, those are values that would be useful to know, but they are on the green sheet for you. Let's take a look at the gas laws. There are a number of European guys that came up with gas laws for us. These laws are actually probably some of the first chemical reaction equations that were developed in the late 1600s, 1700s, when real experimental science started to be done, primarily in the areas of physics and chemistry. Here's our list of the gas laws. Boyle's law. Robert Boyle was an Englishman, and he looked at the relationship between the pressure of a gas and its volume, assuming that I had the same number of particles and things are at a constant temperature. And he found that pressure and volume are inversely related. If I increase the pressure of a gas, its volume will decrease. Monsieur Charles was a Frenchman. He looked at the relationship between the volume of a gas and its temperature. So he kept the pressure and the number of particles constant, so he had sealed containers, and he watched what happened to volume of gas when he changed the temperature in its flexible container. He found that there's a direct relationship between volume and temperature. As the volume increases, so because the temperature increases. Gay-Lussac was another Frenchman, and he maintained constant volume and number of particles of a gas, and what he looked at was what happens to the pressure and the temperature of a gas. Increase the pressure on a gas, the temperature will go up. Decrease the pressure on a gas, the temperature will go down. And if you've ever felt the nozzle of an aerosol can, if you've ever used a fire extinguisher and felt the nozzle when you're done, what you'll find is it gets really cold because you are releasing gas at high pressure, pressure is dropping, and that allows the temperature of the gas to drop. Avogadro developed his famous number by working with gases and looking at what happened to gases when I combined them in fixed masses, meaning fixed number of particles, the temperature is constant. And what he found was that the volume of a gas is proportional to the number of particles I have if my temperature and pressure are constant. So N stands for number of moles in Avogadro's law, V stands for volume. X is some multiple number of moles of a gas. Combined gas law takes Charles' law, takes Boyle's law, puts them together, looks at combining pressure and temperature and its effects on the volume of a gas. And if I take pressure times temperature and divide it by the volume, what I'll get is a constant. If I take all these and I combine them and I take into account the number of moles of particles I have, what I get is the ideal gas law. Everybody's favorite, Pivnert, pressure times the volume of a gas equals the number of moles I have times the gas constant and times the temperature. Okay, again, Avogadro's law comes from stoichiometry of a gas, and when you're working with a chemical reaction and all of your reactants and products are gases, the coefficients we've learned in stoichiometry in earlier chapters refer to the number of moles of particles. When I deal with gases, those coefficients can also represent the volumes of gases, either in milliliters or liters or gallons or ounces. But they are volume quantities as well as mole quantities as long as all my reactants and products are gases. The ideal gas equation comes in handy when I want to try and find other quantities related to the moles or to the pressure or the volume. If I start out with the ideal gas equation, number of moles is simply the mass of my gas divided by its formula mass. If I wanted to find the density of a gas, I can use the ideal gas equation and just do some manipulations. Density equals mass over volume. So if I take the ideal gas equation, if I multiply both sides by formula mass, so now it's on the left side, if I divide both sides by RT, the gas constant and temperature, then what I'm left with is mass on the right. And if I divide both sides by volume, volume now moves to the right and it's in the denominator. So now I have mass over volume, which is density. So pressure times the formula mass of a gas divided by R and the temperature of the gas will give me its density. Also, if I take the ideal gas equation and I know the mass of gas I'm working with and I know the conditions that I have, its volume, its pressure, and its temperature, I can figure out the formula mass of my gas, again, just by doing some rearrangement. So to find the formula mass, what I'm going to do is divide both sides by pressure and volume, that gets it on the right, and then multiply both sides by the formula mass, that gets it by itself on the left. So from the ideal gas equation, I can find a variety of things. The mass of the gas, if I know its formula mass, volume, pressure, and temperature, or the density, or its formula mass, as long as I know the other variables involved. Another one of the laws is Dalton's law. This is Dalton of atomic theory fame, and he also worked with gases, and what he found was that the pressure of a gas depends on how many gases you have in the container. And he found that the total pressure of the gas in the container is actually equal to the sum of each of the individual gases that are part of the container. We're going to use Dalton's law most often when we are collecting a gas over water, because anytime you collect a gas over water, you're going to get some water vapor that gets trapped over the liquid. And if you want just the pressure of your gas, whether it's hydrogen or oxygen or carbon dioxide or whatever you're collecting, you need to know the temperature so that you can subtract out vapor pressure due to water vapor, and then that will increase the precision and the accuracy of your calculations. Mole fraction is also a unit, a quantity that we discuss and consider when we're dealing with gases. Mole fraction of anything is simply the number of moles of that substance divided by the total number of moles of all the elements or compounds in the mixture. It's simply a ratio of moles of what you want over moles of the total. The symbol for mole fraction is the Greek letter chi. It looks like a capital script X. And the reason it's important when we're dealing with gases is if I know the total pressure the gas says in my container and I know the mole fraction that I'm interested in, I can find the pressure of just that gas. And the pressure of the gas I'm interested in simply is equal to the mole fraction of that gas times the total pressure of all the gases in my container.